Hello students, welcome to another tutorial on gas laws. In this video, we're going to work out a question I left you guys with in the previous video. So I hope you guys had time to go through it and tried it, and hopefully you got something. Okay, so we are still just practicing out how to use the ideal gas equations, the laws that we described in the previous video. We have a number of questions we're going to work out. In this video, we're going to work out just 2 examples. And I hope you guys will be able to work them out. It's the same equations, the same principles that we're applying. Yeah, let's dive right into it. So if we look at what we're given here, we're saying one way to cool a gas is to let it expand. A gas at 27 degrees Celsius. So what they're telling us is we have a gas whose temperature is 27 degrees Celsius. And when it is at this temperature, the pressure of this gas is 4,000 kilopascals, which makes it this in pascals, is expanded at a 2 atmospheric pressure. So if it is going to be expanded to atmospheric pressure, then it means that the pressure changes from this value to a new pressure P2, which is equivalent to the atmospheric pressure. Now the atmospheric pressure is 1 atm, or you can take it as 1.01 by, so that's 1.01 by 10 to the power 5 pascals. Now what else? And volume 36 times larger. So they're saying the volume V2 is 36 times larger than the first volume. So if when it was at a temperature T1, the volume V1 was equal to V, then the volume V2 after this change in pressure becomes 36 times larger than that value it had in the first place. So this is why I have 36 multiplying V in the second case and just V in the first place. Okay, now what do they want us to find? What is the final temperature? So they want us to find T2. So here, of course, I hope you guys see already the equation that you need to use. If you do, you can pause the video and try it. That is, if you didn't work it out in the first place. So you can try it out from here. Okay, now let's look at what we have to do. The first step, it's very, very important that you do this when you're going to use this equation. The temperature has to be written in kelvins. Of course, this just becomes 300 kelvins. Okay, from there now, the equation we're using is from the ideal gas equation itself. So P1 V1 over T1, this is equal to P2 V2 over T2. Why this equation? Why this format? Well, we have one gas, and then it's only the condition that is changing. One condition is changed. The pressure is changed from this value to atmospheric pressure, and changing this changes everything else. The volume changes, the temperature changes. So it's a condition of the same thing, that of the same gas that changes. That is why this equation is applied. Now, of course, this doesn't result in any of the special cases that we described. Why? Because all the variables are changing. If the question specifies that at constant volume or at constant temperature or at constant pressure, then would have ended up in one of the special cases or the special equations. Okay, now from here, of course, what we want to find is pressure 2. So we can make pressure 2 the subject of the formula. In doing so, not pressure 2, sorry. The question is asking us to find what temperature 2 is, which is this value here, this quantity. So if we make temperature 2, we can substitute and start working out everything, or we can actually make it the subject of the formula right from here. So if we substitute, we can start by substitute. So if we substitute pressure 1, that's 4 million. This multiply V1. So if you recall, we said V1 is just V. So we place a V there, divided by T1. We converted it to kelvins. It ended up as 300. And then this is what is equal to P2, that's the atmospheric pressure. So we can have 1.01 by 10 to the power 5. And then multiplying V2. V2 is 36 times the initial one. And then this is divided by T2, the one we want to find. So from here, we can make T2 the subject of the formula by cross multiplying. And then, of course, I hope you guys are able to see it. The V cancels out from both sides. This cancels out, it cancels out there. What do we remain with? So this comes this side after cross multiplying. The 300 multiplies, so it goes up by 10 to the power 5. And then this, of course, is by 36. And then the 4 million divides comes down. Okay, so from here, of course, when you simplify this, you get the value of T2 as 272.7. But remember, the temperature I was using was in Kelvin, so even this value I'm getting here is in Kelvins. So if you convert this, if you write it to 3 significant figures, first of all, it comes out as 273 Kelvins. And then finally, I hope you're able to see that written in degrees Celsius, this is just 0 degrees Celsius. So this is the temperature that they wanted us to find. So we're able to cool this gas from some initial temperature of 27 degrees Celsius to 0 degrees Celsius just by expanding the gas. So the gas was expanded from V to 36 times the initial volume. Okay, so this was very quick. I hope you guys were able to follow through. I hope you're able to pull it off as well when you tried it. Let's look at the second example. Okay, so this is our example 2. So you guys can also pause the video with this one, try to go through the question, understand what the question is asking us to find before we start. And then I'll also ask you guys to try it out. Okay, so if you have, we can then start looking at how we can work this question out together. So if we look at what we've been given, we're talking about a piece of dry ice, which is just solid carbon dioxide, is placed in a test tube. It is then sealed off. If the mass of dry ice is 0.4 grams and the sealed test tube has a volume of 22 centimeter cubic, what is the final pressure of CO2 gas in the test tube, if all the CO2 vaporizes and reaches thermoequilibrium with the surrounding at 27 degrees Celsius? So what are they giving us? Well, they're saying we have the mass of this dry ice, which is 0.4 grams. And then apart from that, they're saying that this gas is carbon dioxide. And then next up, we're being given a bunch of other details, like it's put in a test tube whose volume is 22. So let's say the volume of the test tube, can even specify this is of the test tube. This is 22 centimeter cubic. What is the final pressure? So they want to find the final pressure P of the CO2 in the tube if all the CO2 vaporizes and reaches thermoequilibrium with the surrounding. The surrounding T is equals to 27 degrees Celsius. Now, if all the gas is going to vaporize, it means that it's going to fill that test tube. So this volume of the test tube becomes the volume of the gas. Now, next up, this value of the volume, we might just want to keep it in meters. So we want to convert this centimeter cubic to meter cubic. And of course, you guys should be able to convert this without really any problems. So if you're having trouble converting from one unit to the other, you can just comment in the comment section. I can make a quick video on how to convert these units. Okay, but otherwise, when you perform the conversion, you should be able to see that this becomes 0. So we're going to have a bunch of zeros here. So this is going to be 0.00022 meter cubic. Okay, now from here, if we go back to the ideal gas equation, what we have is PV is equal to nRT. So what we notice is we can easily calculate the pressure if we know the volume, the number of moles, this is a constant, we know it, and the temperature. But we realize that we know everything else except the number of moles. Well, we're in luck. Given the mass, we can easily get the molar mass of carbon dioxide. And of course, you guys can use your chemistry. You should be able to see that the molar mass is going to come out as 44 grams per mole. Now, using this, we can then calculate the number of moles using the formula mass over molar mass. And then this is going to give us, it's going to be 0.4 divided by 44. And this gives us the number of moles as 0.0009090909. This continues, can even take it up to that point, moles. Okay, now with this done, we can then go back to our formula. Now we have everything that we need. We have the pressure. The pressure is what we're looking for. We have the volume, we have the constants, and then we have the temperature. So from here, if we get back our formula, we make the pressure that we want to find the subject of the formula. We perform our substitution. Okay, how many of these do I have? One more. So this is multiplying the constant, that's 8.314. And then the temperature in kelvins, 300 kelvins. This is divided by the volume in meter cubic. So this becomes 0. And then we have 22. So of course, if you simplify this, you realize that the answer we get, okay, so if we simplify this, the answer we get comes out to be 103. You can even leave it up to here, or you can say this, that. Just there, this should be fine. So this is in pascals. And then of course, this value is in pascals. You can convert it to other units. You can say this is 10.3 by 10 to the power 5 pascals. You can convert it to ATM if you want it to be in atmospheres. Then this can be written as 10.2 ATM. So you guys should be able to convert from one unit to the other with ease. Again, if you're struggling with how to convert units, you can just comment in the comment section. I can make a video on how to perform the conversions. Okay, so we're still practicing on how to work out how to use the gas laws. This is basically things that you've done, you guys. I can make a few more videos on the gas laws. Otherwise, I think we're going to work out one last question under the gas laws. After we're done with this question, we're going to look at some other interesting concepts. Basically, we're going to go on to look at probably things to do with specific heat capacities. Yeah, those should be more interesting for us to look at. Okay, so you guys can try out this question. Hope you'll be able to pull it off. So again, we're still looking at the gas laws. It's something that is a little bit okay. Just try to think through it. So this is going to be for our next video. Okay, otherwise, we end here. Yeah, I hope you guys found this video helpful. We'll see you in the next video. This was your tutor.